everybody. My name is Abel, and I'm a master's student at the University of Waterloo in Canada, and I work with Andre Lottak on Scala. And today I want to talk to you about algorithmic typing for DOT, and DOT stands for the Depending Object Types Calculus, which is this theoretical model that underlies or specifies the foundations of Scala. Okay, so what's this algorithmic typing thing all about? So we all know and love typing rules, and they're a great way to describe type systems, but there's a problem with typing rules, which is that they tell you what your type system does, but not how it does it. And let me give you an example of that. So on the left, I will show you 3 simple typing rules. For example, the first rule, this is the rule for typing variables, and to get the type of a variable, you just look it up on the typing context. The second rule is for typing addition, and to type addition, we just type the left and right-hand side. We assert that they're both ints, and then we can say that the whole addition term has type int. And finally, this is a very common rule that's called subsumption, and it says that if we can assert that E has type T, and we know that T is a subtype of U, then we can also say that E has type U. And so the exercise that I want to sort of try to go through is to try to imagine how we would go about implementing these rules in a programming language or with an algorithm. And so a type checker is usually implemented with a big pattern matching expression. And so we have our type checking function, and it takes a typing context and an expression, and we're going to pattern match the expression. And let's try to sort of reproduce each of these rules. So variables are quite easy. We just, if the expression is a variable, then just look it up on the context. Addition looks also very similar to the plus rule. So we type check the left-hand side, E1, then the right-hand side, E2. We assert that they're both ints, and then we can return int. And then comes the problem, because there's no straightforward way to translate or implement this subsumption rule. So the first problem is that we don't know what to pattern match, because the E over here could be any expression, so E is unconstrained. And so even if we sort of bite the bullet and we say, let's pattern match anything, right, we'll still have to guess what T and U are. Okay? So there's a lot of work that's been done on dots as a way to model Scala, but all of these papers, so all of the work sort of to date, they all use declarative typing rules. So they all use rules like subsumption that you saw before, which we cannot implement. And so what I'm going to try to do in the talk is I'm going to show you how, if you're willing to restrict your language a little bit, the expressivity of your type system, we're actually able to type check, not all of dot and not all of dsub, and I will tell you what the dsub is right now, but a subset of it. So to sort of conceptualize where we are, so this is sort of the Scala type system, and then there's the dot type system, and you can see that it's sort of a subset of Scala, but not a strict subset. There are some things here. And then there's dsub, and dsub is a calculus, an even simpler calculus, so even simpler than dot, that sort of describes the core of dot. And we have good reason to believe that all of these type systems are undecidable. And so the talk is about really seeing how we can do algorithmic typing for a subset of dsub. So this little circle over here. Okay, so let's review dsub first. And the presentation of dsub that I'm going to talk about comes from a paper by Nadamin and others at last year's Waterloo Fest. So we have terms and types in dsub. So what are the terms? We have variables, lambda abstractions, applications, let expressions, and this thing, which is a type tag. And you can think about it in Scala terms, this would be a type alias. I would say type A equals T. And then when it comes to types, I have bottom and top. So bottom is a subtype of everything, and top is a supertype of everything. I have a dependent function type that goes from S to T. I have a type declaration, right? And what my type declaration expresses is the idea that this type A is between S and T. So S is the lower bound, and T is the upper bound. And finally, there's this thing, this is a path-dependent type. And the idea is that if I know that X has one of these type declaration types, then I can refer to x.a, and I will know that x.a is in this range. So greater than S and less than T. Okay, so there are 2 main problems that happen when we try to go from declarative typing rules in dsub to algorithmic typing rules. And the first problem is because dsub is able to encode an even simpler calculus called fsub, so the second order lambda calculus with subtyping. And yeah, and we know that f sub is undecidable, so algorithmic typing for f sub is undecidable. And we also know that d sub can encode it, so that sort of gives us good reason to believe that if we were to try to type all of d sub, that would be undecidable as well. So that's one problem. The second problem is related to bad bounds. So what are these bad bounds? So in d sub, we can use type declarations inside lambdas, for example, in this way. I have a lambda, variable x, the arguments, and I say that the argument has type declaration A that goes from top to bottom. And the idea here is that inside of E, inside the body of the lambda, I can assume that top is a subtype of x dot A, and also that x dot A is a subtype of bottom. And so by transitivity of subtyping, I get that top is a subtype of bottom. And the problem with this is that now I can prove that any type is a subtype of any other type. For example, let's say I wanted to show that int is a subtype of the function type int goes to int, right? Well, so certainly, and this is sort of the simplified subtyping lattice, right? And the arrows indicate subtyping. So certainly I know that int is a subtype of, and this is the arrow that we added inside the body of E, where we said that top is a subtype of bottom. So certainly I know that int is a subtype of top. And I just said that inside the body of E, top is a subtype of bottom. And certainly bottom is a subtype of int onto int. So that's it, right? And I can do this for any two types. So these bad bounds, so these type declarations with bad bounds are problematic for that reason. And let me be even a little bit more specific. So suppose I have a typing context, and I have three things in my typing context. I have this variable E, and it doesn't matter what E is. What matters is that inside the typing context, I know that B goes to B is a subtype of B goes to C. And now I have a function that has type B goes to B, and a variable that has type B. And then the question is, what is the type of the application F applied to B? And the answer is that there are actually two possible types, B and C. Well, how did we get to each of them? Well, F has type B goes to B, right? And B has type B, certainly. So, just straightforward application. I get that the result has type B. But I also have this statement here. So F has type B goes to B. This is a subtype of B goes to C by subsumption. I now know that F has type B goes to C. And when I get the application, now this has type C. And so it turns out, and I show this in the paper, that you can choose B and C to be unrelated in the sense that neither is a subtype of the other. Right? So we can choose B and C so that, so that F applied to B has each of those types, but neither is a subtype of the other. And what that means is that if you try to implement the D sub typing and subtyping rules in an algorithm, your algorithm or your type checker will have to choose sort of non-deterministically, in some sense, if you will, which of these two is the right type. And sort of in more technical terms, that just means that there's no minimal typing for D sub. And it's a conjecture, so we don't, it's one missing piece, and it's in the paper. So, okay. So there are these two problems that make typing D sub hard, right? But we also know that there are existing compilers that somehow manage to either overcome or somehow work around all these problems, right? So let's take a look at what Dotty in particular does. So a very similar example to what we saw before. We have a trait, bad bounds, and we're going to have this abstract type declaration with a lower bound and an upper bound. So E has lower bound int goes to int, and upper bound int goes to string. And now we have a function f that has type int goes to int. And what we want to test, right, is we want to test if Dotty is sort of directly inferring from the fact that I have this type declaration, if it knows that int goes to int is a subtype of int goes to string, which is what we would expect if we were operating sort of in the D sub world, right? Okay, and how can we do that? Well, simply we can declare another variable f2, and f2 has type int goes to string, and then we can test if we can assign f to f2. Right? And we would expect that the assignment will go through. It will type check if the compiler thinks that int goes to int is a subtype of int goes to string, which it does not. Okay? So that's a little bit different from D sub. But is all the information about the lower bound and the upper bound and how they relate, is it all lost, right? And the answer is that it's not lost. And in fact, we can make this program type check again by adding an intermediate value E of type E, and now sort of F gets assigned to E, and then E gets assigned to F2. And that type checks. Okay, so why does that type check? So this is sort of a very, 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 very simplified version of the subtype routine inside Dotty, right? And you can see that it takes two types, so T1 and T2, and it would return like a Boolean over here. And the question that we want to ask or to answer is, why is it that int goes to int is a subtype of E in the previous example that we saw? And we will answer that question with the help of callers. So, now we have, we don't need to substitute int goes to int for T1 and E for T2, which we will do. So let's substitute T1. Okay. Let's substitute T2, right? And now the compiler, there's like a big pattern matching expression here. The compiler sees that E is a type declaration that has a lower bound and an upper bound. And the lower bound is, from the previous slide, int goes to int. All right, so we plug that in. And now the subtype check will go through because these two types are the same. Okay? And that holds, that's how we get that int goes to int as a subtype of E. And a similar sort of mirror or symmetrical case in the type checker will give us that E is a subtype of int goes to string. But we also saw in the previous example that int goes to int is not a subtype of int goes to string. So subtyping is not transitive in Dotty, sorry. Okay. Okay, so we saw sort of these two problems, these two challenges, the undecidability via f sub and the bad bounds problem. And we also sort of one approach that Dotty uses to handle bad bounds. And so now let's try to formalize all of these in the context of D sub and to try to come up with algorithmic typing and subtyping relations for a subset of the calculus. So we start with the standard typing and subtyping relations, and they're undecidable. And we want to end up with algorithmic typing and subtyping relations, which are called step typing and step subtyping. And these relations, and I will show you how they are derived, but the properties that they have is that they are decidable, they're sound, and by that I mean that if you can assign U some type T under step typing, then you can also assign U the same type T under the standard typing relation, and the same holds for subtyping. They're not complete, right? So there are terms that are only typable under the standard relation, but are not typable under these new relations. Okay, so how do we handle the two problems we had? So one of them was undecidability via f sub, and if we take sort of a deeper look at where exactly the undecidability comes from, so f sub has these universal types that specify just upper bounds, no lower bounds. And full f sub allows you to compare universal types that have different upper bounds. But we also know that there's a simpler version of f sub called kernel f sub. And in the simpler version, the upper bounds are the same. They're restricted to be the same. And that language, that simpler language, kernel f sub, has decidable type checking. And so we can try to do a similar restriction for d sub. And the way in which we do that is we can look at the encoding that maps f subtypes into d subtypes. So this is an f subtype over here, and this is a d subtype. And we see that the universal types in f sub get mapped into function types in d sub, where the upper bounds sort of matched modulo the transformation. And so a sufficient condition to restrict these two types to have the same upper bound is to say that in d sub, in our new version of d sub, we can only compare function types that have the same argument type. Okay, so to summarize, we have this problem of undecidability or potential undecidability via f sub, and the solution is to only allow comparison between function types with the same argument type. And this is based on the approach taken in kernel f sub to make it decidable. Okay, so the second problem is bad bounds, and we saw the example of how bad bounds can sort of throw your subtyping hierarchy out of whack. And so let's see which typing rules sort of conspire to make bad bounds possible. So we have subsumption, transitivity of subtyping, and then we have these selection rules that allow you to sort of reason about a path-dependent type with respect to its lower and upper bound. And the solution here is to get rid of subsumption and transitivity of subtyping. But we can't just get rid of them because they're actually useful for stuff. So let's take a look at what exactly we need to put back in. So yet another example, we have a typing context. In this typing context, we have three things. And let's go sort of bottom to top. We have some variable f that has type y dot b, with path-dependent type. But we also know that b has an upper bound x dot a, and we know that a has an upper bound int goes to int. And we want to be able to type check the expression f applied to 42, right? And so what we need is we need a way to notice that f has type y dot b, which is a subtype of x dot a, which is a subtype of int goes to int, meaning that the whole thing will type check. And the way we do that is with this auxiliary exposure operation, and we read this as y dot b exposes to int goes to int under gamma. And more generally, if we know that s exposes to t, we have two guarantees. So the first guarantee is that s will be a subtype of t. So t is the sort of the result that we get, and t will be a supertype. And the second guarantee is that t will not be a path-dependent type. So the exposure operation allows you to get rid of path-dependent types in situations where you really want to see through them, if you will, and take a look at what the underlying type is. For example, in the previous example, a function type that will allow you to type check the whole expression. And there are a bunch of rules to calculate exposure, but the important part is that the exposure operation is decidable. It terminates, it preserves subtyping, which is key for soundness, and it takes exponential time. Okay, so the second problem can be summarized as we have this issue with bad bounds, and they make sort of the subtype checks, they make it really hard. And the solution is to just remove the transitivity and subsumption rules, and to replace them with suitable uses of exposure where you need to. And this is based on an exposure relation that exists already for f sub, and of the treatment of type declarations inside DOTI. Okay, so what are the properties of the system that results when we replace the standard typing and subtyping relations with step typing and step subtyping? So there's sound, right? And we saw this. So if I can say that t has type t under step typing, then the same holds in the standard typing relation. Same holds for subtyping. They're decidable. They're not complete. Okay. So there exists an increasing body of work on using dots to model different Scala features and reason about them. But all of that body of work so far is not implementable because it all uses declarative as opposed to algorithmic typing and subtyping rules. If we are willing to give away a little bit or give up a little bit of the expressivity in our type system, for example, by not having transitivity, we are able to then come up with algorithmic typing and subtyping rules for a subset of these calculi. And step typing and subtyping are precisely two examples of such rules. And hopefully in the future we'll be able to expand them to handle more of dot and Scala.